morning, ladies and gentlemen. Today, I will talk about my research paper, Crit Fatigue Crack Growth Behavior of P91 steel. I will start with introduction as a motivation to my research, and I will talk about the material that I've used and the experimental testing. And the results of the Crit Fatigue Crack Growth testing can be presented in terms of the fracture mechanics parameter, which is delta K, and the C-star parameter. And I will talk about the crit fatigue interaction under the various frequency. And I will talk about the fracturography and the static electron microscopy. And I will conclude my presentation. So traditionally, power plant components are designed to operate at baseload operations. But nowadays, due to the availability of the renewable energy, the power plant needs to operate in a flexible manner. So this flexible manner, flexible operation means that the mechanical and the thermal loads on the high temperature components are to be cyclic. So this cyclic operation may lead to the interactive trip failure mechanism that is known to accelerate the failure. So therefore, this is important to characterize and understand the crit fatigue behavior of power plant component. So the material that I've studied is the P91 steel. One of them is the S-resist material, and the other two is the X-resist material, which were in the operation for over 110,000 hours and 100,000 hours. So we have performed the microstructure studies, and we have found that both S-resist and the X-resist materials exhibit the large martensite microstructure. So I will talk about the experimental testing. So the crit fatigue crack growth testing will perform under the crit fatigue crack growth testing standard, and the 4 CT specimen has been tested, which is denoted as the CTA, CTB, CTC1, and CTC2. Note that the CTC1 and CTC2 were from the X-resist material, which is contribute to the larger ASTM round robin project. So the CTC1 and CTC2 were fatigue crack to the A naught over W almost 0.4. But for the other two specimens, the notch is created by the electrical resource machining. And the initial delta K is depend on the maximum load. So the crit fatigue crack growth testing will perform using pneumatic load lifting equipment, and the LVDT is used to measure the load line displacement, and the DCPD technique is used to monitor the crack length. So a triangular waveform is used where the loading and unloading will help constant approximately like 2 seconds. And the hold time of 600 seconds is superimposed on the maximum load. And the load ratio R0.1 is used. So the tests were interrupted before the full fracture and subsequently broken open by the high frequency fatigue loading. So the initial and the final crack length is calculated by averaging the 9 measurements along the crack front. So as the first result shown here is the crack extension versus the normalized number of cycles and the load line displacement normalized by the time. So all the tests shows that the steady crack growth from the initial loading. So for the CTC2, which is subjected to the highest load and the temperature, they had the shortest test duration as what we expected. So I've mentioned earlier that the crit fatigue crack growth can be characterized by using the by the fracture mechanics parameter, which is delta K. So in this plot is the crack growth per cycle correlated with the delta K. So under the same frequency, we can see that the crit fatigue crack growth behavior is similar. So in order to investigate various effects of frequency on the crit fatigue crack growth behavior, I have included the data from the literature. So the data consists of the crit fatigue crack growth behavior up to 1 Hz. And I've also included the pure fatigue crack growth data to examine the frequency effect. So to further analyze this result, I have mapped the radiation fit line to the data. So this radiation fit line shows that at the low frequency and at the high frequency. So at the low frequency, at the high frequency, the great fatigue crack growth tend to become the pure fatigue crack growth. And the lower frequency, the crack growth rate increase at the decreasing of frequency and an increase in temperature. This is due to the significant creep distribution. So another parameter that characterizes the creep fatigue crack growth is the C-star parameter. So this plot is creep crack growth rate against the C-star parameter. So to compare the result, I've plotted with the available static creep crack growth data for P91 steel in the range of 600 to 625 degrees Celsius. So we can see that the creep fatigue crack growth and the creep crack growth data is similar, close to each other. And to further analyze the result, I've plotted the creep crack growth data band at 400 degrees Celsius to 625 degrees Celsius, and the predictive and SDW model for the plane strain and the plane stress condition. So we can see here that the creep fatigue crack growth data fall into the CCG data band, and also the creep fatigue crack growth data falls toward the upper bound of the static creep crack growth data. By closer look on the data, we can see that there are some indication that the increase in temperature results the high crack growth rate. And the creep fatigue crack growth also are bounded by the NSW plane strain and the plane stress condition. However, the plane strain condition is over predict the crack growth rate. So in order to investigate the creep fatigue crack growth interaction under various frequency, we have plotted the dA over dN against the frequency. And in this approach, the linear cumulative rule is used by means of the total crack growth per cycle is contributed by the cyclic dependent and the creep dependent. So the material constant for the creep and fatigue is determined by the fatigue crack growth testing and the creep crack growth testing alone. So for this data, the delta K is taken for delta K equals to 30 MPa square meter for the tested data, and for the delta K 20 MPa square meter and 30 MPa square meter for the available data in the literature. So this line, predicted line here, is for delta K equal to 30 MPa square meter and 20 MPa square meter. So at the high frequency, the fatigue is dominant mechanism, and the crack growth rate is insensitive to the frequency and is given by this horizontal line. And at the low frequency, the creep is dominant and leading to the intergranular fraction. At the intermediate frequency, approximately 0.1 Hz, both fatigue and creep are significant, and the mixed transgranular and intragranular fracture is expected. So at the frequency tested at 0.001 Hz here, the creep fatigue crack growth falls within the creep dominant regime. So we further analyze the results by looking at the crack path and also the fracture space. So for the exhibit material tested at 600 degrees Celsius, the crack path is relatively straight-fronted with a small number of crack branches. And for exhibit materials, which is tested at 625 degrees Celsius, the crack grow at some angle. However, for the exhibit material, which is tested at 620 degrees Celsius, a large crack open displacement is observed, and the crack shows some discontinuity of branching, this may indicate that the creep is the dominant failure mechanism. So we further validate the results by the scanning electron microscope. So these pictures only shows for one sample, which is the X-resist material, CTA. So this micrograph shows that the dark region is the creep fatigue crack growth region, which is faceted compared to the fatigue crack growth region, which is flat. So the SEM graph, SEM pictures for the creep fatigue crack growth region indicate that the intragranular fractures compared to the transgranular fracture in the fatigue crack growth. Though are not shown here, similar observation was seen in the other samples. So to conclude, the creep fatigue crack growth behavior of P91 still in S-receive and the X-resist material has been examined. And the crack growth is characterized using the fracture mechanic parameter, delta K, and the C star. So at a high frequency, the fatigue crack growth behavior tend to that of the high cycle fatigue and is best correlated by the delta K parameter, while at the lower frequency, it is best correlated by the C star parameter. So we have used the linear cumulative rules to predict the creep fatigue crack growth in detail by considering the frequency effect. And we have found that it is relatively consistent with the prediction lines. So, and lastly, an intragranular fracture was observed for all the creep fatigue crack growth tests, examined with the frequency less than 0.002, indicating that the fracture is the creep dominant. So with that, I thank you.